we've got 2 kilograms of oxygen that are filling the cylinder of this piston cylinder assembly. Our initial volume and pressure are 2 cubic meters and 1 bar, which you can see right here. And then heat transfer to the oxygen occurs at a constant pressure until the volume is doubled. Now we're going to determine the heat transfer for the process in kilojoules, and we are going to assume specific heat ratio is constant. So remember, that's the K, it's going to be 1.35. And we will ignore kinetic and potential energy effects. Now on this one, we're wanting to find the heat transfer for the process, so that means we want to find Q. Remember, anytime we want to find Q, we're going to go back to that energy balance equation. So if we write that out, we'll have delta KE plus delta PE plus delta U, that's capital U, that's going to equal Q minus W. All right, so we've got that equation. These two terms go away since it said we could ignore those. And now this is internal energy. Usually we're going to switch this over to specific internal energy unless you happen to be given the capital U values. We are not though, so let's go ahead and switch those around. So remember, capital U, when you do the change there, is going to be the mass times specific internal energy at state 2 minus the specific internal energy at state 1. Now that we have this, and we know that K is constant, that means our CV is also constant, our specific heat at constant volume. So let's write that down. So since K is a constant, then CV is a constant. All right. And if that's the case, then we can rewrite this up here as M times CV times T2 minus T1. Because remember, we had the equation that the specific internal energy could be CV times T2 if this is constant. Now we have this relationship. All right. All right, so let's see what else we need to do. We're going to use this when we get back to this equation. We want to find Q. That means we need to look at work now. So let's look at work. Work for these piston cylinder assemblies, you're going to use the integration equation that we've been using. Looks like that. If you go ahead and integrate this, you're going to get the pressure times V2 minus V1. Note that these are volumes. Now let's put this and this into equation 1. So let's call that 1. If we do that and then solve for Q, we're going to get Q equals mCV times the change in temperature plus the work term. So pressure times V2 minus V1. And then let's see what else we need to do here. So this will be our final equation that we're going to get to, but we got to make sure we have all the data. V1, we've got that. V2, we know V2 is twice the volume at state 1. So we can find that one. And T1 and T2, we do not have those. We don't have temperature anywhere in here, so we're going to have to find these things. And then same thing with CV. We don't have a value for that yet. So we'll find that. Mass we do have. That was given right there, so it's 2 kilograms. Okay, so we still got a couple of things left to find here. So let's go ahead and do that. We also know pressure. Okay, so let's go ahead and find T1 first. T1 is going to be P times V1 over M times R. And remember, R is R bar over molecular weight. And this is our ideal gas equation. Okay. Now let's plug everything in. Initial pressure was given as 1 bar. And the initial volume was 2 cubic meters. We're going to put that over mass of 2 kilograms. And then R bar over molecular weight, we got 8.314 over 32 units. Once you do all the units and everything, you get kilojoules per kilogram Kelvin. All right, so now we have that. Now we got a bunch of units going on in here. We got bar, we got cubic meters, kilojoules, kilograms, and we just need the units to be in kelvins. That means we're going to have to do some conversions. First one, let's do 10 to the 5th Newton per meter squared. Put that over 1 bar. And then we're going to multiply that by 1 kilojoule per 10 to the 3 Newton meters. Okay. So once you do all that, it's going to give you the units that you need because the bar cancels out. Cubic meters, notice we got a meter down here, square meter, so all of these cancel out. Kilojoules goes away, and then kilogram goes away right there. And finally newtons goes away. So we got rid of all those units except for kelvins, and we get 384.9 Kelvin for T1. Okay, so now we've got that. And what we're going to do here is, remember this is constant pressure here. That means P1 equals P2. Using that information, we can find T2. Let's go ahead and solve our ideal gas equation for pressure. And then we can set P1 equal to P2. So we're going to have M times R, so that's R bar over M, times T1 over, actually it's V1, that's volume. And then set that equal to the same thing for state 2. So that's what it looks like at state 2. Now these R terms go away, the mass is going to go away because mass is constant, and then you're just left with these ratios here. Now we could solve for T2, and you'll get V2 over V1 times T1, and then just plug in your values. V2 over V1, we know that V2 is 2 times V1, so if you plug that in, you're just going to get a 2. And then for temperature, you're going to get 384.9 because that's what we found for T1. So you get 769.8 Kelvin. Alright, so there's T1 and there's T2. Now we got both of those done. Last thing is CV. For this one, if you look back in your notes, we have an equation that is CV equals R over K minus 1. And we're going to use that equation. So R is R bar over M. So we'll have 8.314. Molecular weight is 32, and then that's going to go over 1.35 minus 1. And remember, units here are kilojoules per kilogram Kelvin. Now when you do this calculation, you're going to get 0.742 kilojoules per kilogram Kelvin. So that's what you get for CV. Now we have everything we need for Q. Now we'll go back up to that energy balance equation, and then we can plug in our values. So Q is going to equal the mass, which was 2 kilograms, times CV, which is this 0.742 number. And then we're going to have the change in temperature, so we want T2 minus T1. Those are both Kelvin. And then after that you have this pressure volume term here. Alright, so I'm going to have to continue this on the next line. Pressure is constant at 1 bar, and then the volume change is just going to be 4 minus 2. Whoops. And then that's cubic meters there. Alright, so now we got that. Notice the units, we've got bar right here. We don't have bar anywhere over here, so we need to convert over to kilojoules. So you're going to have to do your 10 to the 5th Newton per square meter per 1 bar. Multiply that by 1 kilojoule per 10 to the 3 Newton meters. Okay. Now you got that. All your units are going to work out. The meters go away, newtons will go away, bar goes away. You're left with kilojoules. Over here, make sure you also have kilojoules. Kelvins go away, kilograms go away, you got kilojoules. So units are good. Let's go ahead and find our value. And I am out of room here, so let's just draw an arrow up here. You're going to get that Q is equal to 771.2 kilojoules. This is positive, so that means, just like the picture shows, that energy due to heat is transferring in to our system. All right, so there's a heat source out here somewhere, and we're getting some of that energy. It's being brought in. All right, see y'all next time.